Hello and welcome to this quick tutorial on implementing a rigid body based top-down controller. For this we will learn how to grab input using the input axis, which is a nice way to get information that is directional from keyboards or other controller devices. And we're gonna use a rigid body to implement this movement because we want the character to collide with these walls in this Bomberman style level that I have set up. So let's go ahead and make a new script and call this player movement. Go ahead and edit that. And let's say I changed my mind now and would rather like to call this top-down player movement, just to make sure that this class is meant to manage a top-down player. Now I have actually broken my script, so if I go and wait to compile and try to assign this script now to my player, it says it cannot do that because it doesn't contain a class that can be managed by a script. So your file names always have to have the exact same name as your classes inside. So if I rename this now to top-down player movement, now I can assign it and it works again. Now that our class works, we can start and add our variables that we need. We need another float speed, of course, since we are moving and we want to set our movement speed. But this is actually already it. We don't need any other variables. And now an update. We need to ask for the keyboard input that is being pressed, and this is done by using the input axis. We could, of course, also ask for something like get a key down and then ask for the left or right arrow key, but it's actually a lot nicer to use the axis since they are mapped not only to the arrow keys but also to WASD on your keyboard, and they can also take in controller input. They use the Unity input system. So if I were, for example, to ask for the horizontal input axis, like so, I would get input that is either left or right arrow keys, or A or D, or the controller stick being moved left and right. You can see these input settings by going to, let's wait to compile again, to the project settings and to input, or rather the input manager. Here we have an array called axis, and this has the definitions of all predefined buttons and input axis. When, for example, we have the horizontal axis here that is defined by left or right or A or D, and we have another definition for horizontal that uses the controller joystick inputs. And this settings will just gather all kinds of input from any kind of devices that are connected and pipe them directly into the functions here where you can request the data, what kind of input is being pressed. So getAxis will return a value between -1 and 1, depending if we press a negative or the positive defined button, or left or right on the joystick. So let's define a new vector2, which we call input. And we will put the x value to be the return value of getAxis horizontal, and the y value would be the return value of getAxis vertical. Then we can apply this input that we requested to our transform position. So our position would be modified by, let's make a new vector3 here, and multiply our speed by our input x, so the horizontal input, and of course also multiplied by time dot delta time to make sure that we are frame rate independent. And then we do the same for input.y to get the vertical axis. And then 0.0 for z-axis again. So let's plug in some value here for our speed and try out our movement. Great. Now, of course, we don't have any collision yet, so we can like ghost hover through our terrain here and through our level. And we also have another problem, that is that we actually move faster diagonally. So if I move left and right, I will move slower than if I move diagonally. And that is because the input is -1 to 1 on each axis. So if I press diagonally, I will move actually 1 on x and 1 on y. So combined diagonally, that is further than just 1 -1 on one axis. So if we look at a visualization of our input vector, we have the x-axis here as our horizontal input and the y-axis as our vertical input. The input is actually the square root of 1 plus 1, also the square root of 2 if we press both buttons simultaneously to move diagonally. And this is something that you can easily fix by scaling down the vector to a length of 1 if it's longer than that. We also call that normalizing the vector. So let's quickly do that. Simply ask if input dot magnitude, so the length of the vector, is bigger than 1. We just normalize it. So we can just use this normalize function. That is a capital N there. Alright, and now we have fixed the diagonal movement issue. Next, we want to make sure that we cannot move through the walls of the level. And that is actually something that is not such an easy problem, but we have, thankfully, in Unity an easy solution to it. Now, usually if you want to test for collisions, you would have to see, oh, is a wall left of me? If yes, then I can't move left. If a wall is right of me, if yes, then I can't move right, and so forth. And that would be a lot of checks in all kinds of directions, and would take a lot of time to program. So instead, we're gonna make use of the Unity physics system and use rigid body collisions to make sure that we can't move through solid objects. In our level, all of the cubes here, they already have box colliders attached, but I cannot simply add a collider, so another box collider, to the player and then hope that the collision will work. I can still move through the world because a collider itself does not do any collision resolve and displacement resolve. A component that handles these more complex physics operations, that is the rigid body. So let's add a rigid body 2D to our player. And of course, because we are top down, we don't want any gravity. And there's like a bit of collision resolve already working, right? So I can't move through the walls now, but you can see it kind of like glitches around a bit, and it also rotates weirdly if I move around the corners here. If I move the game view to the right here, you can see how the collision box, right, tries to fit with the movement that the script is directing. So what is actually happening is that our script is displacing our object, and then the rigid body tries to make sense of the colliders and tries to displace our object again, so there is no overlap with any colliders around it. So we have two actors here that try to dictate our player where to move. First, we have our script that is setting the position, and then we have the physics system that is trying to resolve any kind of overlap issues with other colliders. And that's a problem. So you don't want two actors to try to determine the same thing. We should let the physics system handle all of it. So we will adjust our controller to use rigid body velocity and set that instead of directly modifying our position. That way, our script will simply tell the rigid body to move in a certain direction at a certain velocity, and then when the physics step executes, so Unity resolves all of the physics, our object will move at a certain velocity that we set, and then automatically resolve any kind of collisions in this same physics step. And we get very nice and smooth movement. The other issue that we can fix right away is the rotation, right? We don't want our player to like weirdly glitch around the corners. And for that, we can simply set the rotation constraint here on the z-axis. Oh, I have to exit play mode to set this properly. Yes. And now any kind of collision that is happening is not actually trying to rotate us, but we still get the weird and glitchy movement from the script and the rigid body trying to set the position themselves. So let's implement rigid body velocity based movement instead. But keep in mind that this is just one way to solve the movement issues, and in an engine as complex as Unity, there's always many ways to achieve your goals. I'm going to show you the one that I consider to be the best to have a rigid body based movement controller. First of all, we're going to need access to our rigid body. We have the component on the game object, and in order to access and modify its velocity, we need to have access to it in the script. To do that, we're gonna make a private field to keep track of the rigid body. That's gonna be, of course, of type rigidbody2D, and I'm just gonna call that RB2D for short, rigidbody2D. And in the start function, we're gonna grab that component as a reference from ourselves. For this, we have the function called getComponent, and that takes a parameter of a type parameter in which we have to give the type of component that we want to grab. In this case, of course, it's going to be rigidbody2D. So what this function getComponent does is that it will look on the game object where the script is attached. So in this case, there would be the player game object here, and it looks on it for a component of the type that we give it. So in this case, it would be rigidbody2D. So every component that we can attach to a game object is also a C# class that we can grab. So we could grab the sprite renderer, we could grab the transform, which we don't need because there is the transform variable already predefined since we need it all the time. And we can grab anything else, the box collider. In this case, now we want to grab the rigidbody2D. And this way that we give it to the function inside the edgy brackets, that is called a generic type parameter. That is a C# thing to call a function with a specific type when the function executes. So it is sort of like a type that is a variable. I think this is enough for now about generics. They are a complex topic and quite powerful in C#, but we don't really need to understand what this really means in order to use the function. So that is a topic for another time. Now that we have access to the rigidbody2D component, we can modify all of its properties, the ones which are exposed here in the inspector, plus all the ones which are hidden, for example, the velocity. So we could modify the gravity scale if we liked so. So I can write rb2d.gravity scale. There it is. And that is true for all of the other properties that the component has. But what we want to do is mess with the velocity to do our movement. So instead of modifying the transform position directly, so relocating the game object in our script, we're going to tell the rigid body to have a certain velocity that will then move our object in the physics update. So we can get rid of this and say rb2d.velocity. This is the one we want to set. And we can see that it is a vector 2. Since we have a rigid body 2D, it has a 2D velocity. and set that to a new vector 2, which would be input x times speed, and then the y component is input.y times speed. So we move into the direction that we press multiplied by our speed. Notice how time.delta time disappeared because the velocity is already declaring a movement in a direction every second for a certain distance. So setting the rigid body velocity does not mean that we relocate our game object every frame by a certain amount, but instead we tell the physics system to move into a certain direction at a certain speed. And this is the velocity. So a velocity of 2 and 2, right? 2 and 2, that would mean we move 2 every second on x and 2 every second on y. And that means no more delta time consideration. We are already frame rate independent this way from the get-go. And we can actually make this a little bit shorter by simply setting the rigid body velocity to our input multiplied by our speed. So C# in Unity, the vector classes have overloaded operators. So we can multiply a vector with a float, and then that will simply execute a scalar multiplication of the vector. And that way we have the correct kind of speed in the correct direction. So if we execute this now, you can see that it does work, right? We can move, and it works quite nicely, but there is a small problem if we move into a corner, and then we kind of get stuck here. You can see now I can barely move around here, and now I managed to get completely stuck, or almost. And that is because the physics system in Unity is not 100% accurate. So if you look at our colliders here, and the physics system uses the colliders, right, to detect a collision, the block of the player is exactly 1 unit in size, in width, and height. And so are the blocks here, left and right. So the player is exactly fitting in between them, since they are also 1 unit apart. But the physics system does not have this 100% number accuracy when it resolves the collision, and the rigid body tries to determine if we have to displace ourselves because there is an overlap that has to be resolved. So it is a good idea to give the physics system just a tiny bit of room for this floating point calculation inaccuracies, so we don't get stuck on tight spaces like this. For this we can just modify the box collider and make it a little bit smaller, like so. That would avoid us getting stuck in between here. But there's still another issue, and that is that we have, for example here, 2 blocks which are directly above each other. And if I zoom in here on the corner, this is perfectly aligned. However, the physics system again has floating point inaccuracies, right? So if I went and kind of move right here at the wall and move up it, it might be that I get stuck on this edge even though I shouldn't. Since, again, the floating point calculations of the collision resolve in the physics system are not 100% accurate. So what you want to do is either to exchange the box collider here for a polygon collider, where you can cut off the edges that would cause us to get stuck, or even easier, I have to exit play mode again to modify the object, get rid of the box collider, and we add a circle collider. And the circle collider we also gonna give like just a slightly smaller radius, so we have some leeway to operate. And now we have very nice and smooth movement, and we can get around the corners without any problem. So the last thing we could do is to make the movement a little bit more crisp. if you would choose to do that for your game or you think it feels nicer. Right now, if I press and then let go, there is just a small sort of fading out of the movement, and that is because the button input is interpolated. So if I let go of the button, it is not immediately resetting to 0. It is sort of gradually fading out to 0. To do that, we go back to the input manager, look for our axis, and modify this value's gravity and sensitivity here. That will determine how fast we interpolate between the values of -1 and 1 if you press a negative or positive button, or go from 0 to full contact on the button press. But this is something that you will have to find out for yourself, what you like best. I'm okay with the default settings for now. That sums up this video. We have learned how to implement a simple top-down controller, first by modifying the transform position directly, and then implementing the rigid body based movement, which is better if you want to have nice controls with the collision of the environment. And to do that, we learned how to grab the input information using the getAxis function from input, and how the input axis array in the input manager from Unity looks like to set this up. Then we learned that you have to normalize this input if you want it two-dimensional in order to avoid moving faster on a diagonal. We learned how to grab components and how the getComponent function works, and how we modify the rigid body's velocity in order to let the physics system handle our movement instead of doing the displacement directly ourselves in update in our script.